Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists, where I make quick turnaround videos for educators and students. If you'd like me to make a video for you, be it at primary school, secondary school, or university level, then comment me below any of my videos or drop me an email. And if I think I can help you, I'll try and fit in making a video or two for you. Okay, I want to talk now about continuous functions. This is an incredibly powerful idea that I'm going to put up here that links a number of things that seem disparate or different. So let's put up a definition, proposition, and then I'll work through it with some diagrams, which I think will make it clearer. I'm using a little bit this book, actually. I'm going to change it slightly, so let's just rub that out. Okay, so let's call this a proposition. Actually, let's call it a theorem. It's so important. We'll call it a theorem. Theorem. I don't think it's got a name. A lot of the theorems in this area have names, but this one doesn't, I think. Let f be a function from, let's do the reals from real m to the reals m. So you might just like to think of just the reals to the reals if you want, just that simple case, whatever they're following. Are equivalent. One, f is continuous everywhere. Two. So this is the definition now. Two is what you will have seen in first year, generally first year at university. I do have a video on this called, or do I? I'm not sure, maybe I don't. Okay, for every point P given an epsilon greater than 0, we can construct, or as they say, there exists a delta greater than 0, such that this is the bane of many students' life at university doing mathematics, this sort of stuff. If x, some x minus, if the distance from x to p is less than delta, then that that implies that the distance from fx to fp is less than epsilon. I'll draw some diagrams in a short while. 3. So now this is the beautiful thing. We now link this up to a sequence, the concept of a sequence. For every point P, for every, for every sequence. So we have a sequence of these x's that approach P. For everything we have then, or then, let's just put then f of xn approaches f of p. Actually, why don't I rub that out and write it on the next line, just so we set this out nicely, clearly. And f of xn approaches f of p. And then the fourth, which is even more amazing, which links it to open sets. For every open set U in, what do we have? Rn, I think we had Rn. The inverse function of u is open. I might actually just write bracket there. So this is the inverse function of the set u. Okay, so maybe what we should do now is just draw some diagrams. Okay, let's do that. So one, we said f is continuous everywhere. So here, probably one way to look at it, this is just the layman's way of looking at continuity, is we have here the, here we have, I'll just do x, y, so this is the reals to the, oh, sorry, y to x. And the idea is that if you have a function where you can just keep your pen on the, if you can keep your pen on the paper as you draw it all the way forever, both ways, well, then it's continuous. This works for simple things, but as we get more and more complicated, this definition, well, this sort of layman's expression, which I've done, layman's explanation, falls apart. Okay, so the second thing was basically saying for every point P given lambda is greater than 0, there exists a delta greater than 0 such that x minus p, the distance from x to p is less than lambda, implies the distance from fx to fp is less than epsilon. Okay, how can we visualize that? Okay, we need two diagrams here, so let's do that. Do that, and then let's do a cross, and then I'll do the other side. Let's draw here and here. Okay, so you could think of this as being the sort of the Rn, and over here we have the Rm, obviously R3 or 4 or 5, I can't draw. And across here, we have some function. It maps a point from here, across to a point here. Okay, so what is this number 2 telling us? It's saying, take a point P, any point, P, and ask someone to give you an epsilon. Okay. So this P has if I go across here, I'll get to some point here, which is FP. And what this is saying, it's saying, okay, so given an epsilon, so someone gives me an epsilon. Okay, so here's an epsilon. This distance here is epsilon. So given we've got someone, I've nominated the P, we've worked out FP because we know the function. Someone has just hurled at me any random epsilon greater than 0. I created this little circle around here that is a ball around FP of radius epsilon. And what this is saying is there must exist a delta. So I'll put a delta here. I'll put a ball around here. And this is delta radius. And what this is saying is that if we now take a point X, any point in here, X, then when I go across here, that Fx must be in the ball. So for every X that is in this ball, Fx must be in this ball. If that's the case, then we say that F is continuous. Okay, let's go under number let's go into number 3. I better rub all this out from a previous video. Okay, this is good. This is where I think this is working out pretty nicely. For every point P, for every sequence xn that approaches P, we have f of x n approaches f of P. Okay, so the way you might like to think of this is, I suppose I could draw my lines again. Let's draw some. Let's go here, and let's draw this across here, and let's draw here. I suppose I could use the same one and just rub out, but maybe that's going to be confusing for people. So, okay. So once again, we've got Rn. And here we've got Rm. Okay, so what this is saying is, imagine we have a situation over here where we just pick a random point P. And over here we have, say, f of P. And we think about having a sequence of these x's that get closer and closer to P. So here's a x1, x2, x3, x4, x5, ... gets closer and closer to P. And what this is saying is that for every sequence like this, where we draw any sequence that approaches P, then when we look across here at the reals with m dimensions, then we must have the fx, these fxn's must approach fp. So what I'm saying is this x1 here, through the action of f, goes to f of x1, and then f of x2 is here, f of x3 is here, then f of x4, x5, f of x5. It gets closer and closer. So that's what we've got there. Okay, and then the last one, which is the 4th, and is really in some ways the most amazing, most interesting, whatever, because we now see open sets. For every open set, you in this would be an Rm, f -1, the inverse is open. Okay, so what does this mean? Once again, I'm going to draw my diagrams. Let's start there and go. That'll work. And then across here, start about there. Whoops, what happened there? Let's delete that. Just make sure we got the pen, yeah. Okay, so this is saying take any open set in U. So the way we could visualize that is just this. And what that's saying is if we take the inverse inverse f of U, in other words, if this is x, then over here I'll just draw a little diagram. Okay, so there's x there, and so we'll put f, the inverse of x, there. What does that mean? It means that if we took across here, we have f. So f, in this case of f inverse x, just gets us to x. So I assume you've seen that sort of idea before. Okay. So what this is saying is if we take every point in U over here, work out the inverse here, so we take F inverse of every single point, we'll get here this, which we call F inverse U. And now this is saying that if this F inverse U, if this turns out to be an open set like I've drawn it, well then F is continuous. Amazing. Okay, so that's all I wanted to say. There's a lot of stuff there. What I think I might do probably overnight is have a think if I can come up with a good maybe example where we can prove something using this. So I'll have to think about that. If you've got any questions on this really remarkable theorem, or in fact any branch of mathematics, then please comment me below any of my videos or drop me an email at coronahelpmathematics@gmail.com.